All right, so here we are again. So why don't we pick it up where we left off yesterday? And what we're about to do is take a quick review of several different functions that you might encounter in calculus, and just remind ourselves what the key properties are. And while we're at it, we may as well look at what the graphs look like, and also understand what the domain and range are. Now, before I do that, I'm going to fire up Symbolab because I find that Symbolab is a very helpful tool for visualizing graphs in calculus, pre-calculus, whatever. Most of the time, we could probably do it ourselves, but sometimes it's very, let's just say it's not as obvious as it should be, or it could be, what a graph might look like. So that's when a tool like this can be very, very helpful. Anyway, so we've got quite a few of them, and you're familiar with all of these, but we just want to quickly remind ourselves how these functions work. You can see we have the constant function, identity, absolute value, quadratic, cubic, reciprocal, reciprocal squared, square root, and finally cube root. Now, later on, we'll be looking at other functions, of course, but we want to start with these. And now, constant function, as the name suggests, means that every value of y is equal to the same value of x. So in other words, f of x equals some constant c. C is any real number. And when we have a case like this, the graph itself is just a flat line. Okay, you can see, for example, here f of x equals 5. That means that no matter what value we have for x, y is always equal to 5. And a quick reminder here that when you have the horizontal line like this, the slope is equal to 0. Why is that? Because if you recall, the slope is equal to change in y with respect to the change in x. And what we're seeing here is that x never changes. And so therefore, as a result, the slope must be 0. Okay. And that brings up another interesting point, that if you have a vertical line, something like this, say this is x equals 3, that means that no matter what y is, x is, or sorry, when x equals 3, y can be anything, literally anything. Okay, so in other words, when x is 0, y is 3, when x is 1, y is 3, et cetera, et cetera. Now, this one has a slope that is undefined. Because x never changes, delta x is 0. Sometimes you see it written with an infinity symbol, but it's just undefined. Now, if you recall from our last meeting, this, whatever this is, I'm not even sure if there's a proper name for it, fails the vertical line test. And so this is not even a function. And of course, that's because if we use one of these graphs, see that every possible y is associated with x equals 3, and this just keeps going on forever. Okay, so every single y on the real number line is associated with x equals 3, so it can't possibly be a function. The identity function, now this is the one where x and y are always equal to each other. Okay, so what that means then is that you have a straight line. Let's take a look at it, where first of all, it crosses through the origin right here at 0, 0. And then after that, when x is 1, y is 1. When x is 2, y is 2, et cetera, et cetera. So here, the slope is equal to 1. Okay, because no matter what we have, let's say, for example, here's the point 2, comma 2. And here's the point 3, comma 3. I'm using a different tablet today, which I'm not used to. Let me just clean this up a bit. So the slope would be delta y over delta x, which, as you recall, is defined as y2 minus y1 over x2 minus x1. So let's think of this as x1, y1, which is 2, 2. This point would be x2, y2, which is 3, 3. So if you plug in these numbers up here, you'll have 3 minus 2 over 3 minus 2, which is equal to 1. Okay, and that will be true no matter which 2 points you choose. And in fact, this is characteristic of a straight line. The slope never changes. It's a constant. Also, the intercept is 0. Okay, so in other words, this is a straight line where m is 1 and b is 0. So we end up very simply with y equals x, or f of x equals x. Okay, so that's the identity function. Now, the absolute value function, you haven't probably seen it in a while. You don't run into this on a regular basis, but it is very useful in certain conditions. And basically what this is telling us is that no matter what x is, y equals that value, but without the sign. In other words, if we have x is 2, the absolute value is 2, but if x is negative 2, y is also 2. So essentially what it does is it removes the sign. Now, interestingly enough, you can formally define this in a very interesting way, which we'll see more of later on. This function, first of all, let me just remind you what it looks like. Actually, it's right here. It looks like a big V. Okay, so for example, here we start with 0, 0. And then when x is 1, y is 1. When x is negative 1, y is also 1. So you have this big V. It's a big V. And the two sides, if you look at this vertical axis, whoops. Like I said, I'm using a new, it's not new, it's a tablet. My usual tablet is not working right now. So I'm using one that I'm not completely used to. So the left-hand side of the vertical axis and the right-hand side are identical to each other. And we'll see this fairly regularly going forward. This property is known as symmetry, meaning the left and the right-hand side of this vertical axis are identical to each other. They're mirror images of each other. So this function has this property of symmetry. And there's a lot of other interesting properties, but what I wanted to show you is that it can be explained or defined in a very interesting way. This, by the way, when you have something like this, with a sharp break like this, it's almost as if it were two functions hatched together. This type of thing is called a piecewise function because the behavior is very different on either side of this origin. And so we can formally define it in the following way. So what it's basically saying to us is this: if x is a positive number, actually, all right, here we have to go over this for a second. I just want to quickly review with you some terminology, and then we'll get back to this for a second. Just as a quick reminder. Okay, so if x is greater than or equal to 0, then x is said to be non-negative. Okay, if x is strictly greater than 0, we say that x is positive. If x is less than or equal to 0, we say that x is non-positive. And if x is strictly less than 0, we say that x is negative. Okay, so I just want to remind you, you want to be very technical. You want to be very precise with your language when you're dealing with math. It's a very, very precise discipline. So x is greater than or equal to 0. We call it non-negative. Strictly greater than 0, positive. Less than or equal to 0, non-positive. Strictly less than 0, negative. So if you look here at this definition of the absolute value function, you'll see that in the top up here, this means that x is non-negative in English. And down here, x is negative. So if, for example, if x is 2, that means that f of x is 2. Now, of course, f of x is the absolute value. And then if x is negative 2, the function, which is absolute value of x, is negative 2, which is 2. Okay, so that's what it actually means. This is what the absolute value function actually means. Okay, it means that if x is non-negative, then the function is also just equal to x. Otherwise, it is the negative of that negative x. Either way, we know that no matter what happens, x is always non-negative. Okay, all right, excellent. Now the quadratic function. Now we're going to spend a fair amount of time looking at these. They show up quite often in calculus and in a lot of applied areas. For example, economics, we see a lot of quadratic functions. So you recall that when you see something like this, the fact that there's an x squared term in here indicates that we do not have a straight line. We have a graph which is called a parabola. Okay, so there's two basic ways in which this can happen. Okay, so remember the formal definition here of a quadratic function is this. So the parabola can either face up or it can face down. That's all we have to choose from. How do we know which is which? It's a very simple matter of the sign of A. If A is positive, the parabola faces up. If A is negative, it faces down. By the way, if you're wondering, if A is 0, then the function is no longer a quadratic equation. It is a linear equation, and it just becomes a straight line, okay? So that's why we don't have to worry about A being 0, because if it is, then we have a straight line. But if A is positive or negative, either way, we have a parabola. And we can get a lot of useful information from these parabolas. So here's a graph of x squared minus 2x minus 15. If you notice here, A is equal to 1. The coefficient of x squared is 1. There's an implicit 1 here. Therefore, it has to face up. Okay. Also, if you notice this negative 15, this is where it actually crosses the vertical axis. You can think of this as the vertical intercept or y-intercept. Now, as it turns out, we're going to dedicate a fair amount of time to finding the minimum value of this parabola and other functions too. But we're going to find out how to determine where the bottom of the bowl is reached, I guess you could call it, after which the function turns up on either side. That is our minimum point. And it turns out to be a very important idea. For any applied area, we often are trying to figure out where's that minimum point. And then we'll see how to do that eventually when we get to that chapter. Okay. Now, by the way, I also want to mention here that there are 2 points here where this parabola crosses the horizontal axis. These are the two solutions. This would be the x1 comma 0 ordered pair. This is x2 comma 0. Oops. x2 comma 0. And so x1 and x2 are the solutions of the function. Okay, in other words, these are the two values at which the function equals 0. And we know that we can find those by either using factoring or else the quadratic formula. Again, this is something we'll often need to do with applied function or applied disciplines, let's say, like economics or physics. Now, with a cubic function, we've added another term. We have an x cubed term in here. Okay, so cubic functions behavior is a little bit more complicated than for quadratic equations or quadratic functions. So you have a situation where the function could literally cross the horizontal axis 3 times. Okay, not always, but sometimes. Like here, this function can only cross the axis twice. Here, it can cross up to 3 times. And in fact, well, I chose in this case, you see, here's one where it only crosses once. Okay, but you'll see that when we do enough of these, what is something you'll often run into that would be a case that we might run into. And here we, of course, have 3 solutions. And with a cubic function, we can have up to 3 different solutions. With a quadratic, of course, only 2. Now, with a linear function, only 1. All right. Now, here's where we get into some of the more complicated ones. A reciprocal function means we have x in the denominator, basically. 1 over x is considered to be the reciprocal function. And this introduces problems because, as you know, we cannot divide by 0. So that tells us that when we look at the graph, the vertical axis, which is where x equals 0, we're never going to see the function touch that axis. In other words, the function here is in pink. I hope you can see it on the screen. And you can see it's getting close to the vertical axis, but it's never quite reaching it. And same thing down here. So the y-axis is what we call a vertical asymptote. Of f of x. And so what that means is no matter how far out we go, if you notice over here, the pink, as we move to the right, it's getting closer and closer and closer to the axis, but it never quite reaches it. The same thing is true over here. Now, it just so happens that there's a second asymptote here. The x-axis is also an asymptote. We call it a horizontal asymptote. The reason for that is because no matter what value you plug in here for x, this ratio will never equal 0. Okay, so we can't divide by 0, as you know, so that leaves out. That's why we have a vertical axis. But we also cannot ever find a value of x, which when substituted into this function, will give us back a value of 0 for y. So that's why x, or the horizontal axis, is also an asymptote for this function. Okay. A couple of other points to note here that the function is restricted to the first and the third quadrants. Okay, if you recall, the quadrants go in a counterclockwise direction. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. I do not know why they go counterclockwise, but that's how they're defined. So all of the function is restricted to the first and third quadrants. Okay, and it makes sense because if x is positive, y is positive. If x is negative, y is negative. That's why all the area, the function only can be in the first and third quadrant. All right. So the zero is defined as a discontinuity. And so we have two asymptotes in this case. Now, by the way, I want to point out, if you go to Symbolab, Symbolab is a very helpful package here. If you type this in, it's not just going to give you the graph, or certainly it will give you the graph, but although you have to ask for it, you can see, yeah, as you can keep increasing or decreasing, it's getting really, really close. This function is getting really close to the asymptotes, but it never quite reaches it. Symbolab always uses these dashes to indicate that it's an asymptote. But up here, they will actually mention it to you. They'll tell you what the domain is, the range, the intercepts, if there are any. You notice how it never actually crosses the horizontal or vertical axis. There's no intercepts, which means, well, we can't actually solve for this in the sense that we can't find a point where y equals 0. What else is it giving us? Oh, yeah, there you go. It's helpfully giving us the asymptotes. The vertical is x equals 0, which is, of course, the y-axis. And the horizontal axis, the horizontal asymptote is y equals 0, which is the x-axis. Wow. Oh, there's plenty more. It can give us all kinds of useful information if you know where to look. Um, Also, by the way, I just want to point out, this is not just for calculus. Look at all these other areas it can cover. So if you're in another math class in the future, or even economics, really, finance, although it's limited in those areas, you can continue to use this to come up with a lot of useful results, and it's completely free. Although there is a more professional version you can buy or pay for, but what we're seeing here is completely free. Now, of course, you know how they're making their money. Look at all these ads. What's interesting about these ads is whatever you've just been looking at on your computer. Well, I wasn't looking at Rare Beauty on my computer, so I don't know where they got that one from. But usually it's related to something you've been looking at on the net. Like if you've been looking at ESPN, for example, there might be an ad here for I don't know, some sporting goods company or something. They're trying to guess what you're interested in, and they'll put those ads there, and they never stop. But that's the point of this. If that's why it's free. Okay, so we don't complain. All right, reciprocal squared. Now this one is going to be similar to the reciprocal, but different in one important way. There can't be any negative values for y, so we end up with this. Okay, so in other words, here, all the function is entirely restricted to the first and second quadrants because, and if x is positive, y is positive. If x is negative, y is also positive. Okay. Now we don't have to worry about x or y equaling 0. That's not going to happen. And again, you can see by these dashed lines, we have two asymptotes. The vertical and the horizontal axes are both asymptotes. Now, when we start studying limits, this will start to become very significant. So we'll keep this in mind when we move into chapter 1, which is our introduction to limits. The square root function. Now, of course, we know here that we must not ever take the square root of a negative number. Otherwise, we end up with an imaginary number. Now, that doesn't mean you can't do that. But in this course, at least, for the time being, we'll focus all of our attention on real numbers. Sooner or later down the road, they'll probably have a discussion about imaginary numbers. But to focus just on real numbers, we do not take square roots of negative numbers. Okay, they're imaginary numbers. So you might recall just quickly, what is an imaginary number? You recall very I hope very clearly that I is defined as negative square root negative I, a negative one rather. So this is known as an imaginary number. Now, if you combine it with a real number, something like this, it is often referred to as a complex number. Okay, so let me show you an example when this might pop up. Remember when we were looking at solutions of quadratic equations and we used the first we did factoring and then we used the quadratic formula and we found two solutions. If your parabola looks something like this, if it never actually reaches the horizontal axis, then here you'll have two solutions. Both of them are complex numbers. Okay. So in other words, if you took one of these cases and you applied the quadratic formula, you'll notice that um, when you have the something like this b squared minus 4ac term will be negative. And that's why this is happening. So in other words, you end up with a negative square root. Okay. But as long as it crosses, the parabola touches or crosses the horizontal axis, you'll have real solutions. But if not, it will have imaginary or complex solutions. Okay. All right. Now, as far as the square root function is concerned, you'll notice it's increasing. Now, by the way, this is Excel. It doesn't do the best job of describing mathematical functions. It's okay up to a point. Let me show you what this looks like in Symbolab. And yeah, that's a little bit better. Okay, so what do you notice about this one? Well, first it starts at the origin, and then it increases at a progressively decreasing rate. The slope of this function is always positive, but it's getting smaller as x increases. So we say that it is increasing at a decreasing rate. All right, so here's the slope. I'm describing a tangent line to these points. And these tangent lines are getting flatter as x increases as we move to the right. So therefore, the function increases at a decreasing rate. And of course, it is then restricted to the first quadrant. Now, the cube root function is different because, as you know, you can take the cube root of a negative number. The cube root of a negative number is negative. So that being the case, there's no restrictions on the cube root function. If you look here, you'll see that there's no asymptotes. And if you notice, since either both x and y are positive or else they're both negative, that's why the function is entirely restricted to the first and the third quadrants. It also has a very unique shape. If you notice, it increases very rapidly, then it slows down, then it sort of becomes a vertical line for a while, and then it starts to rise fairly quickly, but it is sort of tapering off as we go up to the right here. So it's a very interesting function. All right, now we can start thinking in terms of the domain and the range of these functions. So remember what the domain is. It's the set of all possible x values. Or in other words, what you're really doing is you're taking the real number line and leaving out anything that would lead to either division by zero or imaginary numbers. Okay, so in other words, anything that causes the function to become undefined is excluded from the domain. All right, so for example, now this is a parabola. Let's take a look at it. Now, just looking at this graph, the domain is all the real numbers. Which you can write in the following way. This is called interval notation. And it's just meant to indicate that we're covering the entire real number line. Why? Because there is no value of x which could cause division by 0 or an imaginary number. So if you imagine this is the real number line, everything is covered. So for this one, the domain is very straightforward. Now, on the other hand, let's look at this inverse function. Yeah, now we have a problem. X cannot equal 0. But anything else goes. There's no other value of x. Otherwise, there'd be more than one asymptote, by the way. Since there's only the one asymptote, x equals 0, that means any other value of x is part of the domain. So how do you write that as an interval? One way. So this symbol is union, which means you're combining these two sets. These intervals are actually sets. They're infinite sets. They contain an infinite number of values. And so what you're really doing here is this. Here you have negative infinity up to, but not including the 0. And over here, you have everything from 0 up to infinity, again, not including the 0. Okay, so remember the way this works is that around parenthesis like that means you do not include that number. A square bracket means you do. Okay, we mentioned this yesterday. The differences between the different intervals. Let's just quickly run through that one more time. Let's say you're looking at the interval from 0 to 1. Now here, you're not including either of them. Whereas here, you are including the 1, but not the 0. Okay, that's why it's a solid circle as opposed to a hollow circle. Then we have this case where now it's the 0 that's included, but not the 1. Oops. Oh. And everything in between, of course. That's what this is meant to indicate. And then in the last case, they're both included. Sometimes you hear terminology associated with these intervals. This one is said to be open. This one is said to be closed. And these two are said to be semi-open. Meaning, neither both one side or the other is included, but not both. Okay, that's not that important, but you may have heard these terms before, and that's what it means. An open interval means not including the endpoints. Closed means it includes everything. Semi-open, and there's other alternative names too for this, means that it's one side or the other is included, but not both. And again, because an interval is itself simply an infinite set, we can use set notation to illustrate these concepts here, for example, like I said, this is everything except the zero. Now in Symbolab, though, they don't use, they typically don't use this notation. Sometimes they do, but what they do instead is write it, let's see how they write it. Yeah, like they're saying X is strictly greater, less than zero, or strictly positive, strictly negative, strictly positive. Um, it should be clear from the context what they're talking about. All right, anyway. Now this one is a little bit more challenging. Well, yes and no. The the thing is about this one is that you obviously cannot include 5 in the domain because that would lead to division by 0, but there's no other values of X that would cause a problem like that. So the domain could be written as something like this, where the union, again, of course, means you bring the two together. You are including everything except 5. So here you have 5 up to infinity, not including the 5. Here you have negative infinity up to 5, again, not including the 5. Okay. Now the graph it's kind of similar to the other one, 1 over x, except the asymptotes are different. Once again, we have the vertical asymptote is x equals 5. We already know that that can't happen. But it turns out that y equals 1 um, is the horizontal asymptote. There is no value which you can plug in for x that would lead to a ratio of 1. And again, we could prove this, but much later on when we have more, learn more techniques, that the asymptote is in fact 1. Right now, we just have to look in the graph. Now, here's an interesting one. Now, here, remember, we want to avoid having imaginary solutions here. So we know that x can be 3, but it can't be less than 3, because even 2.99999 is not going to work, because that would lead us to a negative number under the square root sign. So that implies that d can be anything from 3 up to infinity. This time we're actually including the 3, because if I plug in a 3 here, I'll just end up with the square root of 0, which is fine. But anything less than 3 is not going to work. All right, so this time we've got this solid circle or closed circle to indicate that it's everything from 3, oops, 3 up to infinity, including the 3. And then with the graph, you'll be able to see right away why this is happening. You can see we start at 3, so x can be 3 here. This is the point 3, 0. And it has the same shape as, remember, we already saw y equals the square root of x. So basically, it's the same thing except shifted over to here. Okay, and again, yes, we're using this notation to indicate that 3 is part of this interval. In fact, I'm just curious to see how Symbolab represents this. Yeah, I mean, that makes sense. Domain is x is greater than or equal to 3. Okay, and then here's the graph. Beautiful. Now, in general, we're going to develop some rules here for the domain and range for these functions. In most cases, it's pretty straightforward. Again, for the domain, you're just looking to avoid x's that cause division by 0 or an imaginary number. The range is just y's that may result from all the different values of x. So here, of course, this is the constant function. You can call it y equals c or f of x equals c, but whatever that c is, the domain can be all x's, but the range is restricted to that single value c. So this is an interval that consists of a single value. This is just saying that the range is c itself, and that's it. Okay. The identity function, if you look at it carefully, you'll see that. Well, that could have been a little straighter, but okay. Um, there's no restrictions in either direction. In other words, there's no value of x that could cause issues, and all values of y are possible. So therefore, the domain and the range are both the entire real number line. Okay. This line, of course, goes out forever in both directions, and therefore, that all possible values of x and y are included in the domain and the range. Now, the absolute value function, if you recall, is this big V. So it starts here at the point 0, 0. And if you notice, there's no restrictions on the x. So our domain is the entire real number line. The range, on the other hand, cannot include any negative numbers, but it can include 0. So we have 0 up to infinity, including the 0. Okay. Now the quadratic function, given that it's a parabola, whether the parabola is facing up or down, the values of x will go on forever in both directions. Okay. If we drew enough of this graph, you'd see that x can go up to positive infinity, down to negative infinity in either case. The range, now, by the way, if you notice in either case, there's a unique minimum point over here. And over here, there's a unique maximum. This is where the function cannot have a value larger than this, whatever this is. That is what's going to help determine the range. And this point, by the way, is called a vertex. Okay, whether it's a minimum or maximum, it's called a vertex. So if you look at it carefully, let's say that the vertex is the point, let's say 1 comma negative 2. That means that the range starts at negative 2, and then it goes up to infinity. Okay, so in other words, it can be any value from negative 2 up to infinity. But on the other hand, if we have something like this, say this is the point 0 comma 3, that means that the range starts at 3 and goes down to negative infinity. So we'll write it like this, okay? Everything from negative infinity up to 3 is a possible value of y. In this case, the previous one, it was negative 2 up to infinity, including the negative 2. So we need a formula that will let us determine this range depending on whether the parabola faces up or down. So let's see. Oh, by the way, as far as the notation goes, it's pretty standard practice to designate the vertex. Let's say again, here's your vertex as h comma k. That's the standard way of doing this. So the k is what we need to determine the range. So here the range will be k up to infinity, and here the range will be negative infinity up to and including the k. Now, of course, we would like to know the actual values of k. Well, it turns out there's a formula for that. Okay. So let me jump ahead. Oh, um, hmm. I thought that I'd include it in here. All right, well, I'll tell you what it is. Um, so given that these are quadratic equations or quadratic functions, the vertex h is equal to negative b over 2a, and that implies that k is simply f of negative b over 2a. So in other words, you can replace, when you have the actual values for your quadratic equation, you can replace k with this information. Okay, so let's look at an example of this. All right, here's y equals x squared plus 2x plus 1. Here's your vertex. So a is 1. Because there's an implicit 1 here. B is 2. C is 1. So that means that h is minus 2 over 2 times 1 minus 1. K is therefore f of negative 1, which is negative 1 squared plus 2 times negative 1 plus 1. 1 minus 2 plus 1, 0. Okay, that means I didn't draw it very well. um, so the vertex is the point negative 1, 0. So see if I can tidy this up. Maybe not. So it looks like it should have been more like this. No, don't worry. I've got the symbol lab graph on the next slide. All right, that'll have to do. All right, so let's see how that really looks. Yeah. I don't know what that red line is doing down there. Symbol lab sometimes puts things in there, but this is what we're aiming for. This black line is the horizontal axis. And so this is the point negative 1, 0. That's the vertex. And the whole point of this is that the range is therefore everything from 0 up to infinity, including the 0. Okay. In other words, y can have a value anywhere from 0 up to infinity. Now this one is the one that's facing down. And we can figure out the vertex. Well, it's already here, but we can prove it. By using our formulas. Okay, and then K is f of h. So you replace all these x's with ones. Um, 2. So yes, the vertex is 1 comma 2. Yes, there's 1 comma 2. So y is never going to go above 2. And so all the y values are here. And so the range is everything from negative infinity up to and including the 2. I'm saving the file because you know what happens if you don't, you can lose all of your work very easily. Now the cubic function, remember the way it looks. There's no restrictions on either x or y. Okay, and that's because we can take the well, the cube of a negative number is negative. So the range of values for both x and y is the entire real number line. Even if you end up with something like this, you can see that it's going to cover all the x's and all the y's. Reciprocal function, it's very straightforward. We already saw this. X can be anything except 0. Y can be anything except 0. Okay. Those are the asymptotes of the function. Then this one, remember, x is squared. So there's never going to be any negative y's. In fact, they'll never be 0. Oops. That's not the best, but all right, there you go. So yes, we've already seen for this one that x itself can be anything except 0 because that would lead to division by 0. The y is, since the y can't be negative, it also can't be 0. There's no value of x that would cause this ratio to be 0. So the range is 0 up to infinity, not including the 0. Square root function. So the x's can be anything. The x's are non-negative, meaning 0 up to infinity, including the 0. So the domain is 0 to infinity. Same thing with the y's. Y can be 0. It can be positive. It can't be negative. So x and y are non-negative, and therefore their domains are everything from 0 up to infinity, including the 0. Cube root. Actually, I think I just drew that incorrectly. Let me go back. It's similar to that, but the shape is a little different. Oh, that's right. It's that one. Okay. All right. Yeah, I knew something was wrong. But you get the idea. You're still seeing a case where all values of x and y are possible. Right? So the domains are for both of them are all the real numbers. Okay, and again, that's because you can take a cube root of a negative number. Now here's an interesting case. Um, yeah, you can see very clearly that x cannot be two. It cannot be negative two. What about y? Well, the ratio here, um, it turns out that this ratio can never be zero. Okay, so we've seen this before. When you have a constant divided by x or some function of x like this, there is no value of x that will cause this ratio to be equal to zero. Okay, so you can see the asymptotes are y equals zero, the horizontal axis, and here x is 5, a negative 5, sorry, it's not, no, it's negative 2. What am I saying? It's negative 2. That would be my vertical axis. So basically that means that the domain is everything except negative 2. And similarly, the range is everything except 0. Okay. Oh, here we go. I mentioned this earlier with the absolute value piecewise functions. You've got two or more regions where we need a different formula to calculate the function. So here's one that you look at it first and you say, well, what's going on here? When x is positive, we have a quadratic function. When it's negative, we have a linear function. What is that going to look like? It's almost like a very bizarre type of case like the platypus, which has all kinds of bizarre parts. But this is what it looks like. So, well, again, this is not the best. The idea here is that this part is linear and this part is cubic. It's really kind of hard to tell by looking at this graph. Now, I know Symbolab is capable of doing this, but every time I try this, it always gives me trouble. It has a separate editor of some kind. And the one thing that I don't like about Symbolab is its own instructions are essentially non-existent. If you want something like this, you basically have to go to Google and it comes back and says, "Oh, you mean, yeah." See now, um, so I wanted to show how it would represent the same graph. I find that it happens a lot. Like Microsoft, for some reason, their own help files are absolutely awful. If I need help with Excel, for example, what did I do? Well, I did something I shouldn't have. Oh God. You'd think that it would be listed up here. If they're going to have it in the functions, where do you see piecewise functions? You don't. All right. So I'm going to be more careful this time. What did I ask for? 3x and x squared. Okay. Oh, I don't. Oh, all right. Not sure it even has an undo function. You have to really be careful with this thing sometimes. All right. So I just want the graph. Yeah, I mean, you can see, this is a little clearer. I see what they've done here. I wasn't expecting this. They've continued this line so you can see where it would have kept going had this all been the same linear function, y equals 3x. But instead, it switches over to y equals x squared. And so you get this bizarre function. You can easily imagine in practice when you would run into this. Let's say that the prices at a store, you're eligible for a discount after you reach a certain quantity. So the price of a product might be, for example, $3 if you buy a small number. And if you buy more than a certain number, the price drops to 250 or something like that. Then you actually have a piecewise function, the price of the good. So it does happen. Okay. All right. Now, here we go. Now, I do want to mention here that this concept of rates of change. Um, we're going to save this for tomorrow, by the way, but rates of change, when we go through this right now, you'll see it looks like a very straightforward idea, but it turns out that rates of change are at the heart and soul of pretty much everything we're doing in calculus. A lot of the results that we get are nothing but rates of change. So this is going to prove to be an incredibly important concept throughout Calc 1 and Calc 2 and all the other calculuses, because in really the techniques that we're using, that's, for example, derivatives, that's all they are, rates of change. So we'll be getting a lot of examples of this as we go along. We'll start with a simple case of linear changes between two different variables, and we'll take it from there. All right, so I guess we'll stop here. Like I said, aiming for an hour per lecture, and hopefully this is all coming back to you. And fairly soon, probably by the end of the week, we'll be ready to start working on the new material, which is limits. Okay. And that's when we're going to be starting calculus 1 as opposed to pre-calc. Okay. And limits, as you'll see, will require us to understand this concept of rates of change. So this is going to prove to be hugely important. So that means you're probably saying, well, we can't wait to see what's coming up next. Well, this will be a very important part of that. All right. Anyway, so I'll stop right here and I'll see you all tomorrow.